All right, everybody, let's go and get started. I'll get the sign-in sheet passed around. All right, so let's sort of recap where we're at. And today's going to be a fairly important lecture, especially once we finish our example that we were working on, because it's going to actually lay the foundation for just about what everything that we do for the rest of the semester. So it's going to be kind of important, at least from a theoretical standpoint. Okay, so what we've been talking about is we've taken a reinforced concrete beam, the idea of a beam, and asked ourselves, if we take that beam and start amping up the load, how will that beam respond? And we've already, assessed one of its responses, the fact that the beam will remain uncracked until the tensile stress reaches a certain point. And we term that F sub r, the modulus of rupture. And we've done a series of examples looking at, well, how does the beam respond elastically, is what we'll say, or how will it respond until we reach the cracking moment. Now, after that, it's not as if the beam can't stop, or it stops taking load. Of course, it can still resist load, but it resists load in a cracked state. And we assess that through the use of a transformed section. Now, I'm defining behavior for you in 3 stages, and what's ultimately going to be the most important to us, and what we'll spend a significant amount of time this semester looking at, is stage 3. What is the ultimate capacity of that beam? How much will that beam be able to withstand before it fails? Okay, and that's what we're going to try and define today. But real quick, we've got this concrete cracked behavior we still need to assess. We hadn't quite finished that. So we were looking at a cracked beam, and we said, well, here's what we're going to do. We're going to use this philosophy of transformed sections. We're going to take all of the regions in that beam that are subjected to tensile stresses and assume that they're completely ineffective because they've cracked. They can no longer resist tensile load because they're separated. All of the concrete and compression we'll assume it's still effective, and for tensile regions, we have our resisting steel. We convert that lump of steel into an effective lump of concrete through the use of a modular ratio, which is the ratio of the modulus of elasticity of steel to the modulus of elasticity of concrete. And we were looking at this example, okay? So I want to go through and go back to our slide, or our notebook or whatever, and go through the math a little bit and make sure that we're clear on what was going on with this. Okay, so we were given this rectangular beam and it was subjected to some load. We need to first determine, are we dealing with a beam that is cracked or not? So we calculate the cracking moment. So the beam's rectangular in nature. That means the gross moment of inertia is easy to calculate. We have the centroidal distance easy to calculate. F sub r, 7.5 lambda squared FC prime. And we can calculate the cracking moment pretty easily, and it's 27 some foot kips. Now, the moment that is applied to this section is much higher than that. So that means that this beam has cracked. It has undergone cracking, and we must use a transformed section to determine the stresses. Okay? Everybody good with this? Now, we then say, well, we've got to assess this transformed section. That's going to be our assumed cross-section for analysis. And, we have a couple things that we need to look at. First off, the area of steel is 3 square inches. Why is it 3 square inches? Because we have 3 number 9 bars. So for a number 9 bar, the area is 1 square inch. We pull that data from our rebar tables to get the area. The modular ratio is the ratio of the Young's modulus for steel and the Young's modulus for concrete. Young's modulus for steel is always constant, 29 million psi. For concrete, if you're dealing with normal weight concrete, as we are in this problem, 57,000 times the square root of FC prime will give you Young's modulus for the concrete. Comes out to about 3 million. So you divide the two, and you get a number around 9.2, 9.3, something like that. When we utilize modular ratios, we tend to take the nearest whole number. So we'll take n to be 9. So remember, we're taking steel and we're transforming it into an effective lump of concrete. If we have 3 square inches of steel, that effectively means we have 27 square inches of concrete. So now this transformed section is all made of one material. A concrete chunk in compression up top, an effective lump of concrete at the bottom. That's the whole point. Everybody good? Okay. Now, that takes care of that. Now we've got to actually start doing some analysis. So in order to do that, we sum moments around our neutral axis, or where the centroid is. Okay? Now, by summing moments, let's take everything above the neutral axis. The area of this rectangle up here is just 12 times x. The centroidal distance, how far is it from the neutral axis to the centroid of this rectangle, we'll say is x over 2. Okay? That's my moment contribution above the neutral axis. Below, I have this lump of concrete, n times the area of steel, multiplied by the moment arm, 17 minus x. Keeping everything in unit or in consistent units with inches, I'm left with this quadratic equation. And I've got to believe you've been able to solve quadratic equations for a long time now. I don't care if you use your Casio quadratic formula, it doesn't matter. You should get 2 answers. Now, we eliminated one of those answers right off the bat because by the very nature of the solution, you will get 1 negative value for x and 1 positive value for x. It doesn't make sense to have a negative value for x. It's not valid. So our x distance for this problem is 6.78 inches and change. Everybody good? Yes, sir. What's that? I'm not sure how to do it on the Casio. You might be on your own with that. I'm sorry. Go to TI. We'll have to figure that out later. All right. Everybody good so far? Again, please, any other questions you got? Okay. Now, we need to calculate the moment of inertia of this cross-section, but we don't need to determine where the centroid is because we already have. That's what x was. That's the neutral axis. So what I'm going to do is I'm going to say we have a moment of inertia calculation we need to do, but it's going to be much shorter than what we've done before. So we have a shape. And for the sake of description, I'll say the shape is concrete and steel. Okay. All right. So we need to calculate a moment of inertia, an area, and a distance. Okay? So let's start off with the moment of inertia. How do we calculate the moment of inertia of a rectangle? BH cubed over 12, right? So in this instance, it's going to be BX cubed over 12. So it's going to be 12 times 6.78 cubed. And I think I tracked the decimals when I did mine, and I got an answer of about 311.83. Everybody okay with this? Okay. Now, for the steel, you'd think you would do the same thing, base times height cubed over 12. But the problem is we never defined how tall this lump of concrete is. And the answer is it really doesn't have a height. Okay? We're just assuming that we have this lumped value of concrete right at this given point. So when we apply our parallel axis theorem, remember it's I plus AD squared. For the steel, we don't get any contribution from the I, it's the AD squared. So what I'm saying is that for this steel, because we're just lumping it at a given point, I'm saying its individual moment of inertia is 0. That doesn't mean we don't get any contribution from it. Now, what do I mean by that? Let's start off with the area. What is the area for the steel going to be? 27. I'll tell you what I'll do. I'll say NAS is 27. Now, how am I going to calculate the area for the concrete? What am I going to do? And I tracked the decimals. I think I got like 81.37, something about like that. Now, our centroidal distance. Remember, when you're applying parallel axis theorem, what are the d values? Let's remember conceptually. The distance from the centroid of the whole thing to the centroid of each individual shape, right? So how far is it, let's start with the concrete. How far is it from the neutral axis of the entire shape to the centroid of that concrete block? X over 2. How far is it from the centroid of the whole thing to where the steel is located? There we go. Remember, I naught plus AD squared. Okay, so for the upper one, you end up getting something like 1247.3. The lower one, 289.5. So even though it didn't have an individual moment of inertia, it actually contributed more to the stiffness of the section because of that AD squared. Summing that up, you end up getting, if you round all your decimals, 4066.7. So therefore, I propose to you that the transformed moment of inertia is 4066.7 inches to the fourth. Is everybody okay with that? Now, let me ask you a question. I propose to you that this is the moment of inertia of this shape once it has cracked. What was the moment of inertia of this shape before it cracked? 8,000. Doesn't it make sense that the moment of inertia should be lower? Makes sense, right? Remember, the gross moment of inertia was 8,000. Because how would you calculate, let me ask this, how would you calculate the moment of inertia of that? You're saying, what, base times height cubed over 12? Yeah. What is the height? I'm saying it doesn't have one. I'm saying that what we've done is just idealized it as a lumped value at a given point. So its I value is 0. That doesn't mean it doesn't contribute to the stiffness of the section because there's that whole AD squared. If we, yeah, for a lump of rebar, for a region of rebar, yes, that is correct. That you are correct. Everybody good? Okay. So I'm going to go ahead and skip over. So I'll say, so just so we have the information from the last slide, so I'll say the transform moment of inertia is 4066.7 inches to the fourth, and I'll say that my x value was 6.2 .78 inches. Just, you know, I'll round it to the nearest hundredth. That's close enough for government work. Okay. The purpose of this problem was to determine what's the stress in the top of the section and what's the stress in the steel. So I'll calculate, let's start off with sigma compression. So let's just recall, how are we going to calculate bending stress? How do we calculate that? It's my over I. Correct statement? Now, what is, for this section, what is M? What is our applied moment? .70 foot kips. That's going to raise some problems, right? 70 foot kips and inches. Not going to bode well together. How do we turn 70 foot kips into 70 inch kips? No. We're not dividing it. That's okay. Remember, when you're dealing with moments and the units are going smaller, we're just multiplying. So 70 times 12 is what? 840 inch kips. And 840 times 1,000 right? We times it by 12 here, times it by 1,000 there. Am I right? I do that right? Okay. Now, you help me out, okay? We've got our fundamental bending stress formula. Sigma equals my over I. So help me out. What's our I going to be? It's going to be I transformed, right? We have moment, but we need a distance, okay? We need a distance. How far is it from the centroid of the hole shape to the worst compression fiber in the section? X. It's X. There you go. Remember, here's what the shape looked like. I'm asking for this distance right here. The distance from the centroid of the whole thing to the worst compression fiber. But we already defined that earlier. We defined that as X, right? So I propose to you to calculate the compressive stress. The worst case is just M times X divided by that. Does that make sense? Okay. So that is 840,000 inch-pounds. X is 6.78 inches divided by about 4,000 inches to the fourth, and we get a compressive stress of, if you plug and chug, 1,400.7. What are my units going to be? It's a stress, so there we go. So that's an answer. Okay. Now this point is a little more subtle. And I know that you did this in mechanics of deformable bodies. It might have been a while since you've done this, but I promise you did. We have something very similar. We have M times some distance divided by I transformed. First question, what is that distance? 17 minus X. Now, here's what's subtle, okay? This formula would work if we were calculating the stress in concrete, but we're not. We're looking for the stress in the steel, okay? What that means is this, okay? We've got to go through and recognize that we did a transformation. We transformed it into an effective lump of steel, or an effective lump of concrete. In other words, if we really want to calculate the stress in the steel, we've got to ask ourselves, the E for steel is so much higher. Because of that, we might have constant strain, but we're going to have a sudden jump in the stress. How much of a jump in the stress? We have to multiply this whole thing by N. Because right there in the steel, because you have a constant strain, because the E value is so much larger, the stress is going to be so much larger. So we've got to multiply that by N. I know my deformable folks, we did that last semester. I know y'all have done that. So we've got 840,000. Yes? Cold. Okay, hold on. We are breaking away from lecture to affect the temperature in the room. It's okay. Oh. Okay. All right. Back to reinforced concrete design, but it's off now, right? Okay. All right. 840,000 inch-pounds. We have 17. Oh, about there. Minus was 6.78 inches. And then we got to multiply the whole thing by 9 divided by 4,066.7 inches to the fourth. Our stress in our steel, if you plug and chug, you get about 18,966.4 PSI. You tell me. Is that straightforward? Does anybody have any questions?
So our N value, we always need to make that a single digit.
Yeah, it's just typical to just round to the nearest whole number. I mean, can you with absolute specificity say that it's 9.2934, you know, whatever? Rounding it to the nearest whole number is fairly conventional.
If you use 9.3 in that case, it would like throw our answers.
It would, but it's very typical to just use the nearest whole number. Like in bridges, I'm always using 8. I never use anything else. So. Everybody good? Any questions? Now, I mentioned this analogy like last semester. You know, if you ever like go to a Mexican restaurant and you open up the menu and you look in the menu and they have items that have the little chili pepper next to it. You know how you got to watch out when you order that item because that item's going to be spicy, right? And how, you know, I know that students probably feel that the curriculum should have a similar chili pepper next to certain classes because that class is going to incorporate the C word. And no, I don't mean concrete. I mean calculus. We will not use calculus in this class. That being said, I'm going to use a little bit of calculus to explain what comes next. So bear with me, okay? The last stage of behavior for a concrete beam. First off, let me back up and make sure everybody's fine with where we're at so far. So in that last example, we had a beam that had experienced cracking, right? The moment was much larger than the cracking moment, so we used a transformed section. Now let's talk a little bit about those stresses. We had about, what was it, 1,400 psi in the concrete and about 18,000 or 19,000 psi in the steel, right? So it's still within elastic behavior. You know, if you're talking about grade 60 bars, it's not going to yield until you get to 60,000 psi. And if it's like 4 KSI concrete or 3 KSI concrete, we're still within relatively linear behavior. But when we really start amping up load is when we're going to start to experience failure. So what is failure going to look like? Well, what we would like it to look like is we want the steel bars to completely yield, and we want to reach the point where the concrete is really starting to experience its maximum strains. So if I start summarizing what concrete beam behavior looks like, we tend to express that through moment curvature plots, like how much moment we apply and how much the beam wants to rotate. We have a linear behavior up until M cracking, then it kind of jumps a little bit. Then we keep applying load, and then we start to see, the bars begin to yield, and we hit failure. What I'm after is what's this maximum capacity in the concrete beam. Now, the problem with what we're going to see here in a second is concrete behavior is very non-linear. And because of that, we need to be able to assess what non-linear behavior means in terms of our analysis. Now, I want to frame that discussion around a very basic example, and I want to look at a beam, and I want to analyze this beam 2 different ways. And we'll get the same answer, but there's a specific reason why I'm analyzing it 2 different ways. You'll see why. So we're going to develop an approach for how to determine capacity of concrete beams. I want to frame it around this. I've got a beam. The dimensions really don't matter, but I've got a beam that's 12 inches wide. It's 20 inches tall. And I want to ask you what moment is required to generate some stress. We'll say 8 KSI. Okay. There's 2 ways of doing this problem. One way of doing this problem is to just use the flexure formula and solve for moment, right? Sigma equals my over I, so solve for the moment, right? We know our target stress is 8 KSI. We can calculate the moment of inertia, 8,000 inches to the 4th. We know the centroidal distance, or we can calculate. You all are familiar with that approach, am I correct? Okay. Now here's a different way of looking at it. Would you agree with me that what I'm asking, what is the moment required to generate a stress of 8 KSI? I'm talking about a bending stress profile that looks something like this. A fair statement? Okay. Now, let's think about this. All right. I propose that you can take this bending stress profile and integrate it directly and get the answer much more efficiently. Now, what do I mean by that? Let's start off with looking at this bending stress profile. One thing I'll point out, and I'm going to do my best to try and draw this 3-dimensionally. I know this is gonna suck, but bear with me. So I'm looking at the beam like this, right? And we'll say that neutral axis is something like that. When you have a bending stress profile, that bending stress profile is applied across the entire beam width. So if I have a bending stress profile, it'll look like that across the whole beam width. Y'all see how I'm going about this? That it's across the entire beam width? Y'all see what I mean? My 3D art sucks, I know. Yes, and it applies across the entire beam width. Okay. Reason why I bring that up is I want you to sort of dissect this calculation with some detail. Okay. Let's look at this upper triangle. What's the area of this triangle? It's 1/2 times 10 inches times 8 KSI. Everybody see it? 1/2 times 8 inches, or 8 KSI times 10 inches. See that right here? Now, I'm multiplying it by 12. Why am I multiplying it by 12? Because that's across the entire beam width. Everybody okay with that? So, is everybody okay with what's going on inside these brackets? Now, how do we calculate moments? We need a force times a moment arm. What is the distance from here to the centroid of that triangle. 2/3 of 10 inches. Everybody okay with that? So that's the moment contribution from this triangle. Now, what about this lower one? Is it going to be any different? So that's where that 2's coming from. My point for bringing this up is there's two ways of doing this problem. Sigma equals my over I, or this. You get the same answer. Okay? Why is this so important? Well, it's important because when you're looking at a beam and you're looking at code provisions, a lot of times what you'll see is not some, especially when it comes to concrete design, especially you won't see things like, here's how you calculate the moment capacity. What it'll say is, here's what the maximum stress that piece of concrete or piece of steel can withstand, and it is your responsibility to determine what the moment capacity is. So a calculation like this is very effective, okay? I asked you what bending moment would generate a stress of 8 KSI. So if I told you, here's this beam, it can only withstand 8 KSI, what's its maximum moment? This is an effective tool. Everybody okay with that? Now, it's effective for other reasons as well. This bending stress profile is assuming that the beam that we're looking at is behaving very linearly, right? Linear behavior, right? The problem is that concrete is not linear, okay? Let's go back a few slides. This is what the stress-strain curve for concrete looks like, right? So if I'm talking about concrete behavior at its ultimate stage, isn't it feasible to assume that at the ultimate stage, the stress profile looks something like this? A highly nonlinear curve, right? Now, the problem is that this was really easy to integrate. It was a triangle. We didn't have to integrate really anything. We just took the area, multiplied it by the centroid. Pretty easy, right? That sucks. That's tough to integrate, okay? And we as engineers have recognized that problem for decades, okay? This is a tough problem to integrate. Fortunately, ACI has developed an analytical model to attack that problem, okay? Now, how did they develop that analytical model? I'm going to give you a little bit of a mathematical background to try and understand how they developed that. So let's just take a moment off to the side and talk about a little bit of math, okay? And I'll keep the calculus downplayed and pretty straightforward. So let's look at this curve. This is the graph of y equals the square root of x. And you all should remember that that graph looks something about like this. Everybody okay with that? So what I want to do is I want to look at this curve from 0 to 1, just to keep it simple. And I want to calculate two things. I want to calculate the area under the curve, and I want to calculate the moment about the y-axis. Now, the reason why I'm focusing on these two values is because I want to look at this problem from an equilibrium standpoint. So I'm thinking sum of forces, sum of moments. Okay? That's why I'm doing this. Everybody okay? So how do you calculate the area under the curve? You take the definite integral from point A to point B. So here on the left, the area under the curve, I'm taking the integral from 0 to 1 of the square root of x, which is x to the 1/2 power. So 1/2 plus 1, over 3/2, or flipped around 2/3. That's how we're coming with this, right? Evaluated from 0 to 1, plug in the top limit, minus plug in the bottom limit. We get an answer of 2/3. So I propose to you that for this curve, the area under the blue shaded region, that's 2/3. Okay? Now that's how we calculate the area under the curve. If we want to calculate the moment, we do the same thing, but our integral has to incorporate a distance. So we include x. We do the same thing, okay? Integrate with respect to x, and we get 2/5, okay? So I propose to you that this curve has an area of 2/3, and then about the y-axis, it generates a moment of 2/5. Is everybody okay with that? You trust me with that? Okay. Now, I'm an engineer. I don't like things to be complicated. I want them to be simple. I don't like nonlinear curves. I don't like to deal with that. What's the simplest shape to calculate the area of? Besides, what do you think? What's the simplest shape? Maybe a rectangle? Base times height or something like that? Okay. I've got two parameters I need to assess, the area and the moment. So what I'm proposing, this is what I'm saying to you. I can create a rectangle look something about like this. And I propose to you I can dimension that rectangle such that it has the same area and generates the same moment. Okay? Now, how do I do that? What is the area of that rectangle? Well, it's base times height, right? What is the moment generated from that rectangle? Well, about the y-axis, it's the area times the centroidal distance. 1 minus half of the width. Everybody okay with that? So I propose to you that I've got these dimensions for this rectangle. I want to determine what those dimensions are such that the area is 2/3 and the moment is 2/5. I propose to you that if you do the math, you'll get this. Okay? In other words, if you look at these two curves side by side, I've got this highly nonlinear curve, and then I've got this nice, pretty little rectangle over here. The rectangle being 0.8 wide, 0.833 tall. I propose to you that those two shapes have the same area and generate the same moment. Okay? Is everybody okay with that concept? I know the calculus is over. Calculus is over. I know. We made it. We made it through the calculus. Is everybody okay with this concept? Okay. The reason why is because this concept forms the basis of how we compute the strength of a reinforced concrete beam. Okay? ACI employs what's called the Whitney stress block approach. Now, this approach has been around since the late 30s. It's not going anywhere. This is how we compute compressive strength, or how we compute strength of beams. It's how we've done it for decades and how we are going to continue to do it for decades. So let's look at this, this beam here for a second. Okay? So I've got a reinforced concrete beam. It's rectangular in nature, and I have an area of steel at the bottom. I make some assumptions. I start off assuming that the steel yields. So if I want to calculate the force in that steel, the force in that steel is the area of that steel times Fy, right? Stress equals force divided by the area. So if I just determine what my limiting stress is, I can determine the force in that steel pretty easily. Straightforward? Now, that doesn't change, that doesn't fix the issue with this highly nonlinear curve. I still have to integrate that. But what I'm saying is that instead of integrating this nonlinear curve, I'm going to substitute this with this rectangle. I'm going to say that this rectangle has a width of 0.85 FC prime across the board. It is always going to have a width of 0.85 FC prime. It is going to have a depth of A. Okay? Now, how do we calculate A? A is a function of the distance from the top of the beam to the neutral axis, C, and this term beta 1. We will take those details one by one. I don't want to throw too much out at you. What I really am after that you understand right now is how we've taken this nonlinear problem and turned it into something that we as engineers like, rectangles. Is everybody okay with that? Everybody good? Okay. If you're okay with that, we're going to calculate the ultimate capacity of this beam. So let's take a moment and look at this beam in some detail. So I'm going to introduce to you today and for the next few days some notation. So the big thing is I want you to make sure that you're understanding what this notation is and what it represents. Okay? So I have a beam that is 10 inches wide and has an effective depth of 23 inches. Okay, does everybody see that? One thing I didn't tell you for this problem is how tall the beam is from the very top to the very bottom. I didn't tell you that, okay? Do you think we need that dimension? No. As you're going to see, it doesn't matter, okay? Now, I have a beam that is being reinforced by 3 number 8 bars. We'll look at that here in a second. And it is made of A 615 grade 60 steel reinforcement. So if I have grade 60 steel, what is my yield stress? 60,000 what? You're there. You're not KSI. That's a lot of, that would be some awesome steel. 60,000 PSI. Okay? Now, one point I will make, and this is going to be confusing right off the bat, so I'll emphasize this. Okay? Let me go back here. So this is my model that I am using to analyze concrete beams. This is a very important point to make. I am proposing to you that the width of this block is 0.85 FC prime and will always be 0.85 FC prime. What will change, however, is this beta 1. Okay. Now, by coincidence, beta 1 is also 0.85. They are not the same thing. Okay. If you have very strong concrete, for instance, if we're talking about an FC prime of 7,000 PSI, this beta 1 value changes. It ends up being, I think it's a 0.7 if you have like 7,000 PSI concrete. That will change, okay? So it's an important point to make that this 0.85 that defines the width of the block and this beta 1 that defines the depth of the block are two different values. They just happen to be numerically the same because of the concrete that we're dealing with. Is everybody okay with this? Okay. Let's start getting into this example because this is an important example to go through. Oh, where'd my... We'll take our time with this because this is important. Okay. So let's start off with a couple things. Grade 60 reinforcement means what? It means that Fy, as we said, is 60,000 PSI or 60 KSI. Is that a fair statement? Okay. Now, we have three number 8 bars. What is the area of steel? 3 times 0.79. Now, is everybody okay with that calculation, and is everybody able to determine where they can find that info? Like how big a piece of rebar is? It's in your notes, and it's also in the appendix in the book. Everybody okay with that? Okay. Now, let's draw this out with a little bit of specificity. Now, I'm drawing this out symbolically for a reason. Okay, so here's my concrete beam. It has some width, B, okay? We've got steel in the bottom, and it doesn't matter how many bars you draw here. We'll say that this is AS, or maybe if I'm consistent with dimensions, whatever. That's AS. That dimension's D. Now, the total height of the beam we call H, but we're not going to care about that for what we do here. Okay. Now remember, when we draw a bending stress profile, theoretically what it would look like is this. We would have some neutral axis. We'll call this the neutral axis. And we define the neutral axis by saying it's some depth C from the top of the beam. That's the notation that we use, okay? Now, theoretically, if I were to define a bending stress profile, it would look something like this. It'd be like, nonlinear, something like that. And this would all be compressive stress. Then I would have some contribution down here from tensile stress. All right? That's my theoretical stress distribution. Right now, I don't care about that. I've got to be able to use something. So I'm going to draw the real stress distribution here on the right. All right, so what's the real stress distribution look like? Again, I am converting that nonlinear curve into an effective rectangular distribution. You all follow with me. How wide is this curve? It is 0.85 FC prime. Now for now, all I care about that you understand is how tall this curve is. And what is the term for how tall? We say it's A. Now, one thing I'll point out. There is a difference. And again, this doesn't really matter so much right now, but it's going to matter really soon. There is a difference between the top of the beam to the neutral axis and the top of the beam to the bottom of that compressive stress block. Okay? From the top of the beam to the neutral axis, we call that C. The depth of the stress block, we call that A. Okay? Everybody all right with that? And lastly, don't forget, we have this stress and tension at the bottom. Okay. So let me ask you this. I want to look at this from a force standpoint. This steel is going to be in tension. How do we calculate that force in tension? I'm talking about force, not stress. I'm talking about force. How do we calculate the force in tension? We know the area and we know the yield stress. I'm assuming that the steel yields, so what's the force going to be? $60,000. Okay, so my point is, would that be a fair statement? That is the tensile force in the concrete beam. Is everybody okay with that? Now, I did the easy one. You do the hard one. Okay? This compressive stress block, I'm saying that we can idealize that as a compressive force C. I can do a little better than that. What is the compressive force? It's the same deal. We're talking about a stress times an area. I'll ask you the easy one. What is the stress level in this compressive block? How much stress is in that block? No, okay, you're close. It's not FC prime, it's what? 0.85 FC prime. 0.85 FC prime times what? Times the area of that block. What's the area of this block going to be? AB. Because it's A tall, but it's applied over the width of the beam. Is everybody okay with that? Let me see something real quick. Okay. Is everybody okay with that? Okay. This is important, so I'm taking my time with this, and we're going to stop today. We're not done with this example. We're going to spend a little bit of time with it. But is everybody okay with what we've done so far? Not yet. And ultimately, let me say this. Beta is not going to matter really very much until we go back and start checking strains and start looking at ACI requirements, which we're going to calculate the strength of this beam and then go back and check some ACI requirements. No, that's fine. That's fine. All right. We'll see you all next time.